Yes, sir, and welcome everyone.
Thank you. I appreciate you being here. And then his partner, James Schenck. James, you are in Montana, are you not?
I am, Bozeman, Montana, and great to be here. It's a great honor.
Well, we appreciate your taking the time to come and educate us on all of this state-of-the-art information that we are looking at on these systems. It's fantastic. This is a fantastic time to be alive. Dave and I have often said that, having started out with just plain and simple boilers and then moving on from there to what we have that has more brain power on it than the ships that we're going up to and back to the moon again, is a pretty amazing time to be alive. The name of our show is From the Boiler Room, but it's changing. We are soliciting new names for this show, and the current next runner is Boiler Talk, which seemed like a pretty good idea until I got you two on here, and we're not even talking about boilers. So maybe we should call it Energy Talk or something else. But in any case, we do have a contest going on. I am your co-host along with Dave Yates. Give some rules of the road. As you check in, if you would please use headphones and boom mic if possible. That avoids the possibility of having any kind of internal feedback that would blow everybody's eardrums out. And I've asked that you please mute your mic to avoid feedback and background noises, which I've gone ahead and taken care of on my screen, but as people pop in, I'll miss them. And if you have a question for these folks, if you wouldn't mind writing it down on a piece of paper during their presentation so that you don't lose track of your question. And then at the end, we will open it up for questioning the two presenters before we go into our open Q&A sessions. I think that would be very helpful, and it would allow us to get through this process pretty quick. They've got quite a few slides here that they're going to be presenting to us. Questions in regarding to the presentation will be responded to after the presentation, and then we will go into our open question and answer format where you are allowed to bring forth any hydronic problem that you have and see if our excellent group of attendees as well as our host and co-host can at least head you in the right direction. It's virtually impossible to see what it is that you're doing, but we'll get you close to it. Mr. Yates.
Good morning.
There's a good picture of Mr. Yates.
It's in the back of our barn where we keep all of our used radiators.
Man, that's
in the
got to be...
background, you can see the old potbelly stove that the founder of our company back in the early 1900s would break up the wooden skids and crates that things came in, and that's how they would heat the shop.
That's how I heat my shop. But instead of using pallets now, I burn old lawyers.
Fundamentals of Radiant Design is an online program that I'm currently teaching on the behalf of the RPA, and it's through Heat Spring Learning Institute. So, as Mark is often fond of saying, I'm older than dirt. Been in the trade for over 4 decades, and write for Contractor Magazine, Green Mechanical Contractor Magazine, and I've been a member of the RPA not since its origination, but shortly after that. Next slide, Mark. So we talk about the practical application of the heat loss calculation on a room-by-room basis. Go ahead and click, Mark. And heat emitters, equivalent direct radiation on a room-by-room basis. And go ahead, Mark. And what we're trying to do is to match the EDR output temperature and use outdoor reset to its full advantage. Go ahead, Mark. And we want to trim all that built-in fat. Every program that we use to calculate heat loss and heat gain calculations, and also for sizing circulators and systems and pipe sizing from start to finish, has a lot of built-in fat. It's been our experience that that runs anywhere from 10 to 30% over what our best calculations show. Next, so can we use thermostats with setback as well? And with the new boilers, we can. Next slide, or next click, Mark. A lot of the new boilers have a feature called boost, which we can tell how long we want it to wait before boost kicks in. But what boost does is allow us to program in a higher water temperature than the outdoor reset curve would call for, and allows us to use setback thermostats and come back from deep setback with modulating condensing boilers and with a well-adjusted outdoor reset curve. Next bullet point.
kind of like putting the pedal to the metal, get up that hill that you can see coming at you, huh?
This was the York rescue mission, and this was a steam system. It's an old, pretty sad stack looking boiler. Had been originally coal, was converted to oil, and then later converted to gas, and was literally eating these folks alive. Next slide, Mark. So how easy is it to go from steam to hot water? It's actually relatively easy, or you can go from hot water to hot water. In this slide, this was a hot water boiler that had 3 zones. You can see that the water feed's not in the proper location. We're pumping towards the boiler and towards the expansion tank. So it's very easy to make a conversion from a standard chimney vent boiler to a ModCon. Go ahead, Mark, next slide.
I've got a question for you in regards to this drawing. Did this system have a tendency to overpressure itself quite a bit?
I'm sorry, what was the question?
Did this system have a tendency to overpressure itself quite a bit?
Yes.
I can see why. That pressure reducing valve at the inlet to that pump is guaranteed overpressurization, especially when it's pumping towards the expansion tank.
It's actually this easy. You just simply connect the supply and return together to create the secondary loop. In this case, we relocated the zone valves to the returns. We installed an ECM variable speed delta P circulator on the system so that it would react to the zone valves. We installed the water feed on the point of no pressure change where it belongs. And on the primary loop, we put in a 3-speed circ. And in that way, we can move the water through the boiler at the correct rate without any problems. So in a case like this, we would expect to see a minimum, and I want to stress the word minimum, 30% reduction in energy consumption for this property. Mm-hmm. In many cases, however, we'll see as much as 70%.
Whoa.
Next slide, Mark. And this is where we went from steam to hot water in the rescue mission. And we cut their fuel bills by more than 70% in this case because the old boiler was horribly inefficient. You can see we did an indirect water heater with this boiler. They've got, well, a lot of homeless people stay there, so they've got 6 showers that supplies, and it gets very heavy use. And they have no problems with running out of hot water, which they did have that issue prior to that with an 80-gallon gas water heater. They would run out occasionally. Next slide, Mark.
Hey, what am I doing there? Well, I guess I'm up next. Well, I did want to thank you, Dave, for that course that you put together, and we've got another slide coming up here pretty soon asking people to go check out your course. And I can tell you that if you're wanting to learn from one of the world's best, you would sign up for this course, and I guarantee you that when you come away from this course, you're going to be very comfortable going out into the world and looking at all the different types of radiant heating systems, whether they're panel radiators, cast iron radiators, floors, walls, ceilings, whatever, and we'll have a good handle on how to apply it and how to make it work. And we seem to spend a lot of time running around chasing people making things work, and that's one of the goals of the organization, is to teach people how to do it right so that we can alleviate Dave Yates' service calls on Saturdays so that he can stay here and talk to us on this show. So there I am. I am Mark Eatherton. I am your Executive Director of your Radiant Professionals Alliance, have been for about 1 year and 8 months now. It's amazing how fast time flies when you're having fun. I've been a member of the organization for the last 20 years. I've been contributing editor to the Contractor magazine for as long as Mr. Yates, so however many years he says he's been doing it, I've been right there with him. He and I both signed on with them at the same time. Is that like 13 or 14 years now, Dave?
Yes.
That's amazing in itself. I've been an educator for life. I don't know how I ended up picking that part up, but anytime I can teach somebody, I will jump at the opportunity and give them the benefit of my time and experience. I'm a former expert witness. It was basically some lawyers that I used to work for that turned on me, that caused me to decide to get away from lawyers and no longer be an expert witness. And the opportunity to come to work for the RPA hit at a perfect time, and so here I am. I am a licensed master plumber in the state of Colorado, and I am a big fan of alternative radiant panel heating systems. This is one of the very first ones that we did. We did this in conjunction with the National Renewables Energies Laboratory on a Habitat for Humanity home, and it works fantastic. It's tied to a solar thermal system. As you can see, we basically put this at a 4-foot height to avoid anybody finding tubes for us as it pertains to pictures, and ended up insulating that wall behind that because it is an internal wall, and that's one mistake that a lot of people may make when they're dealing with these radiant walls. They think, well, you know, I can heat both directions. Yeah, you can if you want it, but that room on the other side is the bedroom, and they didn't really want a whole lot of heat there. There's another panel. You can't really see it real well from this photograph, but there's another panel back there that will take care of that bedroom quite well. So insulate behind your panels, even if they're in a wall. This is the radiant ceiling of the house that I'm in right now that nobody yet has guessed exactly where it is that I'm located at, but if they do, I will be sure and announce that we have a winner. That is a Ray house system, I'm sorry, a Roth panel system, and was originally designed for application on a floor. I put up 1/2-inch plywood, and then I put up this using some large fender washers, and then I screwed 2 layers of 5/8" sheetrock to that material. And the reason that I went with the double 5/8 sheetrock is because I do have a solar thermal system that's tied to this, and I wanted to utilize, when I'm not here, which is most of the time during the week, I use the solar thermal to charge the sheetrock, which helps carry the space through the night without having to fall back onto any of my other auxiliary heating systems. So here's our one and only brief commercial. We want you folks to join the Radiant Professionals Alliance. If you are not yet a member, ask that you please join. It's fairly inexpensive. It's $300 a year. As a contractor, that allows 3 people to have seats at functions like this. So I think when you stop and take into consideration the fact that you've got 3 employees at $300 per year that covers all 3 of those employees, it's pennies per day. And we have a lot of different programs that we have coming to the forefront. We have the Uniform Solar Energy and Hydronics Code, which will be coming to fruition within the next 6 months. We have the Certification Standards program that we're putting together for hydronic radiant designers and installers, and this will be an ANSI recognized certification. This is going to carry quite a bit of weight. About the talk show, name the show contest. We have a $50 gift certificate waiting for the person that pops up with the best name. The deadline on this contest is November 7th, 2014. The show is currently slated to run every other week with guests being interviewed, and that generally will take probably about the first hour, and then after that we open it up to the open question and answer session where you can bring in whatever problems you have anywhere in the world on any system, regardless of whether it's steam or hot water, and we will do our best to help you crack the special codes on that to get you straightened out. These programs will be archived, but it will be available to members only to review at a later date. So if you would like to see this, and currently these shows are free for anybody that wants to come and participate, with priority seating being given to those members of the organization. But if you want to see one of the archived programs, you're going to have to become a member to be able to do that. Our very important mission on these programs is to have these shows be fun, educational, entertaining, and most importantly, fun. I appreciate everybody taking their Saturday mornings to come in here to not only contribute but to listen and to learn, and seems to be working quite well. I think we're gathering some good steam, and we've got some excellent people lined up to do some interviews with. We've got Ray Wolfarth, who has agreed to come on. I talked to Mr. Richard Trethewey the other day, and he's agreed to come on with his boys, tell us what's new in their life. I just didn't realize until I was talking to him, Richard's been doing this old house for 35 years. It's almost longer than I've been plumbing. I didn't realize he was that old. I thought Dave was the oldest plumber I knew. And by the way, Dave, I don't believe anything that John Barba says about you being older than dirt. I do believe the potential that you invented dirt, but hey, you know, we all got to start somewhere.
That's right.
Hydronic news you can use. We have the Sci-Fex West Trade Show coming up in Alberta, Calgary, Canada. And I'm going to be there. Mr. Holohan's going to be there. John Siegenthaler's going to be there. And Robert Bean's going to be there, along with Mike Miller, who is the new chair of the Canadian Hydronics Council. And a whole lot of very good, interesting people. If you're in the area, I would strongly suggest that you consider attending this. This is like the show to be at for the folks up there in Canada. Mr. Yates, are you going to be teaching at this show?
No.
The OASP?
Oh, the OASP, yes, absolutely. Monday.
Talk about it.
Well, it's going to be on converting steam systems to hot water, and also we will cover outdoor reset curves. We'll do connected load surveys, heat loss calculations, and basically walk folks through the process from start to finish so that at the end of the 3 hours, hopefully they'll be able to take that information and turn that into productive work and go out and earn more money.
I guarantee you, if nothing else, you will pique their interest and they will join one of your classes somewhere. Wish I could make that show. One of these days I will. We also have the Gas Networks 2014 Fall Educational Program, which I believe also starts Monday, but that's further up the coast, up in the northern climes of the New England states, if I'm not mistaken, and our friend Tim McElwain will be there, and I believe Mr. Holohan might be there too.
And Dan's going to be at the OASP show as well.
Is he? He's a busy
Yes.
guy. Then we have the AHR Expo, which will be occurring January 26th through the 28th. The RPA has hitched their wagon to the AHR Expo wagon. We will be there in full regalia with our System Design Showcase Awards program, along with 6 educational programs that are going to be very unique. This is not your run-of-the-mill, this is what you do to install tubing. These classes are going to be cutting edge. As an example, how to obtain net zero using hydronics, how to sell hydronics. That's one thing that most everybody needs to learn how to do. Some very interesting courses coming up on that we're still currently in the process of developing with our education committee and Max Rohr. And then we'll also hold our annual meeting, educational programs, and be electing some officers. Actually, we'll be re-electing some officers because fortunately for us, they've all decided to stay in their current positions. The RPA University's fall course offerings, we have the Fundamentals of Radiant Design, which is the excellent course that Dave put together for us. We also have another one that has been put together that is basically on integrating solar into hydronic heating systems, and that's being done by Vaughn Woodard. Vaughn actually sits on our Uniform Solar Energy and Hydronics Code Committee, is a very knowledgeable person, has done a lot of hydronics, does a lot of PV as well as solar thermal, and he's got some excellent courses that will be coming online. And we also have a lot of other contributors that are bringing courses online, including myself. I'll be doing an advanced course in hydronic heating and cooling, and hope to have that up within the first quarter of 2015. And Ray Wolfarth has agreed to come on board and do a class on commercial boilers and how to interface into those, which I think is a fascinating subject. That's kind of where my roots come from. And just a whole bunch of different stuff coming on. So whenever you get a chance, check into the RPA University Fall Course Offerings. You can get there by going through heatspring.com and then click on the RPA University button, which is a large round green button, and it will take you to where you need to be. Today's guests, we have Colin Wunder and James Schenck with us. Colin, why don't you go ahead and step in and tell us a little bit about yourself first. Actually, let's let James do that. Seems as how I've got James slide up there first. James?
Fair enough.
Sure. Well, I'm very grateful to be here, very humbled, and there's not much to say about me. I guess that is relevant to this. I started out I went to a diesel tech school originally, and then I went to work offshore and worked in the engineering department of a seismic vessel that surveys the underground of the ocean for oil. And you get a lot of experience working offshore with a variety of systems. And you know, I've worked for Energy Dynamics now for I think 4 years, and I'm the territory manager of Montana and Wyoming. And during that time, we've been pursuing this thermal battery concept, and I'm really excited to be able to be here and be talking about it today.
Well, we're honored to have you here, and having listened to you guys the other day when we were doing our dry run, I think these folks are going to come away with some very interesting information on these systems. Colin, tell us about yourself a little bit, please.
Oh, I'm a 38-year veteran, plumbing, heating, electrical, refrigeration contractor. Not quite graduated from the School of Hard Knocks. I came to work at Energy Dynamics 6 years ago, and do tech support and work with the geothermal industry, which is our bread and butter at Energy Dynamics. Done everything from laying pipe in ditches, doing excavating, to building houses, to hydronics. Radiant has been my passion since the late 70s and early 80s, and then I always wanted to marry geothermal to radiant, low temperature water source to low temperature delivery. I remember a conversation I had with Mr. Eatherton back in early 80s, and wondered why I ever wanted to do such a thing. And Mark paid me a compliment just a few years ago that I wasn't quite as nuts as everyone thinks I am. But
we haven't checked in with your wife yet either, though.
She would agree with you that I'd be nuts. But
I say the jury's still out on that one, Colin.
Yeah. It is. I'm a kind of a wild hair in the industry here. But anyway, when James came on board, we were kicking around some stuff, and I wanted to figure out a way to marry geothermal with solar, and ways to tie that together. And James had been thinking along those same lines, and our other partner, whom is not here today, but Brandon Darnell, we all got together and started brainstorming, and came up with this concept, and we put it into practice, and we're totally astounded by the results that we're achieving. And anyway, here to share with you the advantages of a thermal battery system.
Well, you know, one thing that you have that's a secret that I didn't know is that you're a master electrician.
In the state of South Dakota, I hold a South Dakota Master Plumber's license and a South Dakota Class B electrician's license. It's farmstead, residential, anything related to agriculture I can touch, but I can't get into a commercial locker plant. But
keeping you out of the 3-story high-rises there in downtown Carthage, huh?
Yeah. And I can't wire an elevator in a city of Carthage, but
I'm sure you probably could. You could probably show the local electricians how to do that. You've got enough experience in relay logic that you get it. But people that have a background in electric have always impressed me because they have an automatic understanding of the hydraulics that we deal with. It's like automatically there. It's like, you get this? Oh yeah, it's the same thing we deal with. Wow. Okay.
I've run similarities. In fact, at some point I'd like to put together a presentation on the similarities between hydronics, electrics, and HVAC as far as duct. You change the names, you change amperage, voltage, and to CFM or GPM, and head, and static, and they're all equal. The math is the same.
Yep.
Change the names.
I hear you. That's great. You forgot to mention one thing. Colin is also the chairman of our Public Policy Committee, which is probably the best kept secret within the RPA. These folks are basically charged with the responsibility of monitoring all legislation at all levels, and they do that through our folks at IAPMO in Washington, D.C. They have a computerized program that scans all of the legislative information coming out from city, state, county, and federal government, and if a keyword pops up that catches their attention, then they can go in and look at the legislation and see if it's pro or negative, and do we want to support it or do we want to resist it. And Colin is the chief of that particular committee, and thank you for your time and volunteering for that, and I look forward to some of the legislative actions that we will be putting together in the near future, especially after this show, and also in talking to some of the folks that I ran into back there in Tennessee that have some excellent products that are not receiving the support that it should from the federal government, that swing green drain waste heat recovery system, I think, is fantastic. I think every house should have that on it as a minimum. You're reducing the people's energy consumption for domestic hot water by 60% for, you know, a minimal investment that shows a return on the investment in a very short period of time, and nobody's recognized it yet. I mean, it's been around forever. I've got it in my house up here in the mountains, and that's a part of why I'm able to operate without any auxiliary system during the summer months up here. Between that and my solar thermal system, I get no utility bills. If I can figure out how to spin that propane tank backwards, I'll have it made. Well, thank you, Colin.
We'll work on that.
I appreciate your...
James will be working on that, Mark, for you.
Okay. Thanks, James.
Yeah. Yeah.
So, as we've noted here, please hold your questions for James and Colin until after the presentation. Write it down so you don't lose track of it, unless you deem it really, really, really important, like you catch us saying something that's really not true or something, in which case send me a personal message, and I will slow the guys down and say, oh, wait a minute, you know, just because it's light outside doesn't mean the sun's up. So, without further ado, as they say in showbiz, James, are you ready?
Yep.
Let me get this puppy to forward. Here you go. Just talk to me and tell me when to move.
Okay. What we're going to be discussing is this. It's an alternative approach to renewable energy HVAC systems. I guess next slide, please. And we've already talked about who we are, but we both Colin and I work for Energy Dynamics, and our other founder of thermal battery systems is Brandon Darnell, and he owns owns Energy Dynamics. Next slide, please. I wanted to start off with this quote by Stephen Hamstra. We're a fan of his because he kind of gets out there and pokes the geothermal industry. It's kind of like we do, but he's also out there doing it and earning great awards. And I'll just read the quote. As we continue our trek towards cost-effective net zero facilities, our industry is beginning to embrace the concept of shifting from real-time HVAC energy plants, such as boilers and chillers, to systems that capture, store, and distribute thermal energy. So that's just a relevant lead-in. Next slide, please. Okay, so setting the stage here, clearly Colin and I and Brandon come from the geothermal or ground source industry, but we're going to be using this presentation to demonstrate why we would make the assertion that there really isn't any such thing as a geothermal or a ground source heat pump. They're just applied to those things, and they could be applied to multi-sources and multi-sinks. So if we're going to back up and take a high altitude look at this, the game is moving heat around. We're simply trying to source and sink energy out of the structures and in and around the environment outside. So this whole presentation will be on the source/sink side of the system rather than, I think, what is mostly discussed by the RPA, which is going to be distribution elements. And as far as we're concerned, that's an excellent tie-in, but our focus is remaining on the outside or the source sink side of the system. So we'll be spanning several HVAC sub-industries with what we're going to be talking about, including solar thermal, the geothermal, and the air source sub-industries. And I'd say that each one of those is going to have their own unique perspective that if it's taken by itself and it's not seen from the angle that we're trying to come at it from, we might say some things that would be deemed the wrong way of doing things, and then people would want to shut down and not listen to the rest of it. One example would be generally people who are solar thermal minded would want to slap you if you tell them you're going to put a tank in the ground and not insulate it and hook it to some solar collectors. But likewise, the geothermal industry would tell you, that'll never work. You can't just put a tank in the ground and put a heat exchanger in it. You're not, the thermal capacity is too condensed. So we're going to get into some of that, and I'm just wanting to set the stage. Next slide, please. So the common approach to HVAC, you know, we generally think heating means taking a substance and converting it, you know, to heat, changing its form, in other words. So burning something, importing fuel to a site and burning it. Modulating condensing boilers, of course, as this group knows, are the highest efficiency means of burning things to create heat. But it requires that energy to be imported to the site and then for you to change the form of it on the site. And then you need to figure out another set of infrastructure for cooling. Next slide, please. So heat pumps are thermal energy conveyors. So the only difference between a ground source heat pump or an air source heat pump or a air to water heat pump, or, you know, it doesn't matter. The heat pump itself has a high side and a low side. It's absorbing BTUs in on the low side and rejecting them out the high side. So it's just a matter of tying heat exchangers to either side of the heat pump and then figuring out how you're going to get the energy in and out of either side of it. So heat pumps don't know or care where the heat came from, and they don't care where it goes when it leaves. So single source systems, like if we are to accept the arbitrary designation of ground source or geothermal heat pumps, we're accepting only one source sink element, and there's energy in other places. So multi-source, multi-sink systems are dynamic and adaptive. They can actively adapt the source sink side of the system in order to better serve the overall energy loads. Next slide, please. Okay. So essentially, when we, you know, are in the geothermal industry, but we saw a lot of reasons that the industry has trouble gaining market share. It has trouble winning jobs when it's compared to air source systems or other renewable technologies. And, you know, we were in the business of wanting to sell more heat pumps. So, it just seemed logical that there were reasons, even open loop variant reasons, where you'd just put a heat exchanger in a tank. Let's say you had some well water available, but not enough to do a straight open loop system. Well, a simple open loop variant of a thermal battery was one of the applications that we thought was worth pursuing, and so we went down the road of sort of openly developing and pursuing this hybrid application, and that's what we encourage the rest of the industry to do also. We're not approaching this from a proprietary system standpoint. We're saying, much in the way that the standards were developed that the geo industry goes to today, there can be standards that are developed for hybrid multi-source or thermal battery type systems. Next slide, please. So some of the realities of ground source as it is currently understood: it's expensive, it's invasive, there's physical and legal limitations with the site, and there's a very heavy reliance on the competency of the installer or designer. In other words, you know, I don't know how familiar the people in this group are with geo, but it is a process much like the, you know, hydronics in the distribution, and if it's not done right, it's not going to function very well, and there can be all kinds of problems to try to work out with it. So training and all that are very important, but there's another side and another way to look at that is there any way we can standardize or come up with methods that are more scalable that remove some of that front-end complexity?
And you know,
slide,
James, a note on this point. Dave and I have both served as expert witness, unfortunately pursuing really nice people doing silly things in the field that didn't have any training. And one thing that I've been running into recently is people that are doing the slinky loop in the ground. A change in moisture in that soil content will totally wreck the ability of that loop field to be able to produce energy. And that's something that a lot of designers don't take into consideration. And in speaking to some other international ground source heat pump people, I recommended that they put a perforated Tremie pipe into that trench so that if they in fact do lose their moisture because of drought or whatever, that they have an opportunity of being able to go back in and recharge at least some of the moisture in that thing to give them a better bite on Mother Earth. But yeah, that's definitely
Absolutely.
a problem.
If you want to back up a quick second on that one,
Sure.
Mark, too, I might interject one, too. If you take note of that particular picture in there for that slinky design, you will see that those circles touch each other but do not overlap each other other than where they cross, to go to the next loop.
Mm-hmm.
And that is called a 0-degree pitch. Or there's no overlap. An 18, that happens to probably be a 3-foot wide ditch, possibly 4, but if it's a 3-foot wide ditch, an 18-degree pitch would be an 18-inch overlap, so half of that circle would have another loop in it. And the whole key to a ground heat exchanger is being in contact with the ground. And if you're doubling up on that, you better well be in some awfully wet soil conditions, because you're not going to have enough pipe in contact with earth to get the heat that you need. And I'm old enough to remember the days of a 600-foot ground loop being standard, even as short as 400 feet of pipe made into a slinky, and those systems didn't work too well when it got to be January in South Dakota. So then the system kind of went to 600. It's pretty much standardized now at 700 feet per ton with a slinky type design, and we've got numerous people from Wyoming to the Dakotas and Nebraska that are doing it with 800 feet. The old rule of thumb was to add an extra loop. Rather than adding that extra loop now, they'll put 800 feet of pipe in per ton, and they work fine. And same note, depending on soil conditions and where you're at, I also strongly would recommend the trimming pipe as a soaker unit. Used to put them in, did more verticals than I did horizontals, but since being at Energy Dynamics, had the opportunity to go out on a problem system a few years ago. The system was 16 years old and never running hot temperatures in the summertime. They happened to had put in a trimming pipe. We put 30,000 gallons of water in the ground. System started working like a champ.
I'll bet. It's amazing what a little bit of moisture does to conductivity.
Yeah, it is. So back to you, James.
Sure. Well, and I think that discussion, just right in of itself, is evidence of all of the variabilities that exist as just a reality on the front end of the geo industry. And while training can mitigate some of those, you can't mitigate all of them, and there's just it's a reason why the industry has so much trouble gaining any real market penetration.
And every industry has its issues, and I'm glad to see that it's not just on the distribution side, but it's also on the collection side that these issues come up. We've got a lot of education and training to do.
Absolutely. Well, just building heat exchangers into the earth in of itself is a fairly variable proposition.
It is.
So the air source heat pump is the other side of the other game player here. If the game is moving heat around, and we're talking about the source/sink side of the system, then the only other recognized game in town that does that, the only other player, is the air source heat pump. So they're less invasive, they cost less, they have lower performance, they are a good solution for mild climates. The load dictates the time and the severity of the fight, meaning the outdoor unit doesn't get to decide when it's going to come on and begin trying to derive energy out of the air. It's told when to come on by the inside unit, which is a really unfortunate circumstance to be that outdoor unit, because the reason that the load exists is because there's a deficit of energy outside. So it's as if the enemy, the load, gets to pick the terms of and time and place of the fight, and it always is on terms that are in its favor versus the terms of the unit that's outside.
Yeah, it's kind of like solar. When you need it the most, you get it the least, and you better figure out how to work around that.
Exactly, and no amount of inverter technology is going to change the physics of that. As we say, you can't out-technology physics. But, I mean, we do concede they can operate down to zero, and we see a lot of boastful claims of manufacturers talking about how well they work in cold climates and so on. I'd encourage anybody to get out their engineering chart and look at the capacity of these things when it's cold. They are not, when we're looking at tonnages and we want to see how much capacity can you have. Now, less efficient, this group would understand it better than any. It's the opposite of an outdoor reset curve. So it's that as it gets colder, their capacity gets lower and their efficiencies get less. Next slide, please. So what is a thermal battery? Thermal battery is it's a concept, but it's an intermediate thermal storage and exchange element. And a latent capable thermal battery is able to access the thermal energy of the phase change of water to ice. It could, certainly the term could also include a thermal battery that included an exotic phase change material, a paraffin wax or a salt that has a higher temperature range of phase change. But we did a fair amount of research on that. I have quite a few samples of some exotic phase change stuff from a company called Rubatherm in Germany that I got actually even before I went to work for Energy Dynamics. But we've tested some of those. We've done some math on them. Water is a tremendously hidden in plain sight thermal energy exchange and storage element. So these can be achieved by polycistern tanks or concrete cistern tanks with an internal heat exchanger, and it provides an inexpensive and consistent thermal foundation for multi-source sink systems. So it provides the foundation. It's the thing that we get to interact the other elements with. And this is one of the crucial misunderstandings that the geothermal industry would have about it would be, they'd say that'll never work, it's too contained. We're not saying that the battery itself is the source of energy. Now, if it's buried in an uninsulated burial, which we would recommend it would be, even though we have insulated previous ones, that was for the purpose of data logging and for isolating each element of energy that would come in and out of them. But it provides this thing that the industry has not had before, which is a very consistent thermal foundation, the front end, the thing. You put a heat exchanger in a tank of water and you define what that heat exchanger is going to be like and how it's going to work, and it will perform the same way every time. So that was one thing we thought was might have some really big implications for the industry. And while we didn't set out to do this from a standpoint of thinking it was going to change the geo industry, we sort of did it thinking it was going to be another tool in the toolbox. But my perspective on it now is that it is much bigger than that. So it's less invasive, it's a lower installed cost, it's very predictable and scalable. It can be modeled and sized according to the load profile and the climate, so I could select exactly where in the country this is going to be going in, and then our simulators that have access to 30 years worth of solar insolation data and 30 years worth of weather data and everything else, we're getting much better at being able to model with very high degrees of accuracy how these things would perform. So it readily absorbs the low-grade heat from these different sources, and heat, as we say, heat is where you find it. It does not discriminate. If there's a source of thermal energy that can be derived from the environment or recycled from the home or any waste heat process, then that's energy that can be a contributive aspect to the overall usage.
And that's exciting to me. If I've got a block of ice that's sitting there at 32 degrees Fahrenheit going, throw some energy at me and see what happens, I can find a lot of energy.
Exactly. It's as if it's down there saying, try and freeze me, see what happens. As soon as you start to look around your environment, if your starting place is 32 degrees, you'll figure out you can find a lot of sources of energy to contribute at that point.
Yeah, air temperature, snowmelt that has been heated up by the sun could be dumping energy in there. Solar thermal. It's limitless, really. It's amazing.
Exactly. Next slide, please.
There you go.
There we go. Okay, so it's difficult to deplete it. Now, that phase change aspect is not a theoretical one. We weren't really sure how big of a deal that was going to be before we went and did it, but it's a really big deal. So in the next slide, we'll show that in a graph, but let's just go through the math here. The soft landing, as we call it, is the latent heat of fusion. It's 143 BTUs per pound. So 2,500 gallons is 20,750 pounds of water, which obviously would be 20,750 BTUs per degree when it's liquid. But when it gets to 32 degrees, it's 143 times that 20,750 pounds of water, which means it starts acting like 357,500 gallons. Very difficult to deplete it. It rides out the heavy loads and it recovers when they relent. It accepts the low-grade heat. And the shallow earth heat is continuously passively absorbed. It's always recovering to some extent when it is below the earth ambient temperature. Likewise, it's always recovering to some extent when you're in the air conditioning mode and it's buried in the earth, because it's always got heat energy being pulled out of it by the earth. Next slide, please. So there it is visualized. This is the system that's in Laramie. There's currently about almost a dozen of these systems that are actually out there. But this system and Colin's system that he has in his own house were the first two that were put in, and they were both put in the fall of 2011. But in any case, this is the last year. This is 2013-14 winter. We're looking at November 1st there to March 15th. And you can see 4 dead flat locations there where so the green line is the thermal battery, the blue line is the transfer tank, and you'll be able to see a schematic of what this looks after that. But anyway, point is, those dead flat lines are when it's acting like 357,000 gallons. It's very difficult to deplete it. And you can see in the I guess it's the first bit of December there. Those are where the blue line is dipping under the green line. That's when, you know, the battery is got ice all over the heat exchanger. The loads are extreme, and the heat pump is serving those loads. And the solar is trying to contribute, but there's not a lot of solar being able to contribute. And you can see that the very heaviest load existed there would have been that first bit of December when we had that blue line down to 30 degrees. So that's the coldest it ever got. And the blue line would be representative of the entering water temperature to the heat pump. It's the transfer tank, and again, you'll see how that's piped later to see how that all works. And then you can see that at the end of February, we then climb out of the latent phase entirely, and we don't return to it. And then we also shifted the solar over and begin doing domestic water heating, and we're not even putting any solar energy into the battery during the latter part of this graph. And we also stopped putting it in at the front half of the graph. So where you can see the big drops happening, that was actually because the solar was being designated to heat domestic water because the battery was in a condition that it did. So, next slide, please.
James, I have a question before we go away from this one. I see some deep green spikes coming off of that green and blue. Are those indications of the storage system actually taking a big nosedive down below 20 degrees Fahrenheit, or are those just anomalies in the chart?
No, yeah, those lines going clear to the bottom are the data logger being offline, losing connection. So they're just like blips in the data. They're not actual, meaningful.
That's what I thought. I get the same condition in my data loggers too. Yeah.
So to get another representation of how much energy is in that tank, a 50-degree tank that's 2,500 gallons, which I didn't say on here, but that's what we were referring to. Again, it would be 20,750 pounds of water, which is 20,750 BTUs per degree. So if you take 50 degrees minus 32, and you have 18 degrees of energy from 50 to 32. That represents 373,500 BTUs. And then when you hit 32 degrees is where you've got almost 3 million. So.
Hey, Dave Yates?
Yeah.
I think I may have discovered a new use for that empty 300-gallon propane tank that's sitting out in front of my cabin here.
All right, next slide, please. So there's Colin's wonderful demo unit. That's at our Energy Dynamics dealer meeting this last spring. It's a working unit. It's got a little mini thermal battery there with a little mini heat exchanger inside it that's not sufficiently sized, but that's not our fault or Colin's fault. There's only so much you can do in a tank that sized. But this thing is, you can see the little mini solar collector with the light array above it. We've got our web-connected controller running it, and I was able to let guys from the show go by, and I could give them the login information. And with their smartphones, you could log onto the controller. You could see all the system status. We've got temperature sensors all over it. You could see what all those were. And then I had an output labeled God mode that they could turn on and off the sun from their own smartphones. So you could, and I don't know, it's a fun, engaging demo there. And indeed, you can see the ice buildup on the lines leaving the source, the loop side of the heat pump there, and all over the outside of that tank. It had run for 30 hours continuously at this point. The entering water temperature to the heat pump was in the teens, but it was still operating. It had not locked out on low pressure yet, and we were starving it of energy. We weren't even really leaving the solar on much at all. And yeah, just a really neat little demo. Colin made that aquatherm tank out of obviously a big piece of aquatherm pipe. You could maybe tell them a little bit about that climatherm there, Colin. You there?
He stepped out for a cup of coffee.
He must have. Okay. Well, in any case, he had that.
There we go. Sorry about that.
That's all right. You want to tell him about that that climatherm, Colin?
Yeah. Aquatherm built that to our specs. It's a 12-inch Aquatherm climatherm pipe capped on the ends, and then I built the headers that came off of the unions from that point to do what we wanted to. This one was adapted a little bit different than what we have normally done, and depending if this is looked at as a straight drain back solar into that tank happens to be a non-pressurized, although it's the way we configured it, it could be made for a pressurized system or non-pressurized system. There's a gauge tube on there to see what your water level is, rooms for relief valves and fill ports, pressure gauges, and whatever if it is a pressurized system, and a thermal well to tie into our control system for the thermal battery system. The 3 pumps you see, one is for the heat pump from the transfer tank, the other one is for, there's to the far right you'll just see a single ground loop, which this was built to kind of mimic the system in Laramie, and the other pump on there is to the solar collectors, which uses that transfer tank as a drain back tank. It can also be adapted. The actual Laramie project does have a heat exchangers and such in place, and my particular system has a drain back tank with a heat exchanger, so it's piped a little bit different than this. But we were getting ambient energy was more than anything what was keeping that. You can see the frost on the thermal battery, and of course how cold it was going into that little 18,000 or 12,000 I should say BTU heat pump. But the transfer tank was sweating. In a normal application that would all be insulated, but the battery would not be buried in the dirt, and it would have insulation on top to the level of the frost line, but the bottom and sides below frost line would normally be exposed to the ground. In this particular picture, the only place that system's gathering any heat, and that tank was froze solid. The very, very center of that tank had a little bit of water left in it. Great place to set your beer and cool it off. But from there, it was just gathering energy from the surrounding environment in the room.
And by the way, the folks from Aquatherm will be one of our guests. I've spoken to them about coming on and showing us the state-of-the-art fusion socket welding that everybody is ranting and raving about in these mechanical rooms.
I made them scratch their head a little bit on this one. They, because this tank has got some dip tubes in it, and the way it's made, and they stepped up to the plate. Great folks to deal with, and you know, we're hoping to use more of these in the future. I did find that if you see that green solid at the top and bottom of that tank, this one happens to be a non-pressurized. There's a black on top of that. If you see it as an access port or plug, that top is as thick as what you see, and trying to cut that with the Sawzall was a pain in the rear.
Bet.
So,
James, are you ready to keep moving?
Yep. Yeah. Let's keep going.
Get the slide advance forward. There you go.
There we go. So this is a solar array that I took a picture of. This is at a middle school in Douglas, Wyoming. I don't know anything about it. I just took a picture of it because obviously the whole backs, the ladder, third level, is all the panels have been taken down and they're all stacked there. And I'm familiar with another commercial solar installation here in Bozeman that was installed. It's not quite as big as this one, but it's very large. And it was decommissioned about 3 years or 5 years after it was put in, and it's been non-functioning for the past 30-plus years. And I just think these systems are a tragedy, and they're a tragedy that need not occur. You know, they're representative of the applications of solar thermal being used at high temperature delivery. At least I'm presuming in this case that that's what this one was. I know that that's the case in the solar application in Bozeman. And the point that we're trying to make is solar collectors. Well, let's just go on to the next slide now. Make it there. Next slide, please.
Slide advance. There it goes.
Okay, so the challenges and valuation of solar thermal and space heating. We all know that the source availability is opposite the load, and that the capacity of the system is application dependent. In other words, you can't just look at a collector and say that solar collector is good for X number of BTUs. It depends on how you're applying it as far as how many BTUs you're going to get out of it. And the valuation or the return on investment that somebody is going to invest in that solar collector, the other side of that is how much work are you going to get done with it? How much capacity will it have? Now, the solar, obviously, the greater the delta T for the greater amount of time, the greater the capacity that the solar collector can provide. So now specifically referring to the applications that we're applying them at, we can achieve over 100% solar efficiency because the solar collector can be an ambient absorber, which means it can run at night, which is somewhat academic, but it actually does do it occasionally, and it's pretty neat to see it if the pump is running and the sun is not up yet.
It's moonshine.
Yeah, and the idea is, I think we can help make people understand it a bit more if we say, you know, if we ask the solar collector to give us heat, that's a different thing than asking it to melt ice. And it can melt a lot more ice in a lot more conditions than it can make heat. So just restating the first point there, that the source availability is opposite the load demand, when the loads are the greatest, the sources are the scarcest. So what we would want is to have source energy elements that could adapt and gather low-grade energy, you know, sort of in a sliding scale, to where, as the load and the load increases and the energy deficits are increasing and the overall system is depleting in temperature, we want to scavenge energy from anywhere and everywhere we can. And in our applications, we feel like we do a pretty good job of that. And in temperature direct to the distribution solar thermal applications, which is what we believe makes up 100% of the current industry thought about how you should apply a solar thermal collector, you know, that perspective, we would challenge it. We would say, you know, solar thermal directly to the load is certainly the most efficient, but it's not the most, it doesn't have the highest capacity. By putting it in the source side of a thermal battery and using a heat pump, you can get a lot more heat out of them. So, next slide, please.
One thing that I see that is kind of intriguing at this point in time is the SRCC standard that they use for rating solar collectors is not looking at a chunk of ice at 32 degrees Fahrenheit as a storage tank. And
right.
I can see if, as this moves forward, we're going to need to have two classifications for solar thermal collectors. One in a conventional high temperature application and another with ice storage. And I think that the numbers on the ice storage system is going to make those solar collectors look very efficient.
At the onset of this endeavor of ours, we asked the solar collector that we happen to be using in these projects manufacturer what the output, what we could expect. You know, how many do we need? And you know, said, well, you know, what are you doing with it? And I said, well, you know, this is the temperatures we're going to operate at. And they says, well, you can't run them down that low. Well, why can't we? Well, nobody does that. And we, you know, what's the output? And they said, we have no data to support those kind of temperatures. I tell you, it's very interesting when, in fact, there'll be a slide coming up later that I can refer to, but when you fire up a solar collector drain back tank and it's, you know, 35 degrees outside, and this is pure water. There's no glycol, and depends on how you pipe this, but my particular system has no glycol in it. It's pure water. And the first time that happened, I was a little nervous. It's been running 3 seasons now, and I've never had a problem. And it's interesting to see that happen.
I
think it's the next slide here you can go on to. And
I think this is a game changer from a lot of perspectives.
To clarify something Colin just said, he doesn't have any system. The thermal battery in his case is the drain back tank, and the solar collectors do receive just the straight water that's in the battery. But like the other systems, the ability to be latent capable and to be able to freeze the battery, he does have an internal heat exchanger in the tank that is freeze protected, that's on a closed loop that goes through the heat pump. But I just want to clarify that in case anybody misunderstood and thought that all the fluid was the same fluid. It's not. There's freeze-protected glycol. There's also just plain water. So
yeah, yep. Thank you very much for bringing that to light, James.
Yep.
That'll pop up in later pictures.
So yeah, these are Colin's collectors, and as you can see, they're covered in frost. They're also got shading, and as I understand it, this is pretty early in the morning. And when this picture was taken, the solar collectors are running right, and they're putting a charge. They're melting ice inside that battery, despite the condition that they're in. So I don't know if you want to add to that, Colin. Or?
That's about the sum of it. This was about I want to say would have been in. I meant to look it up before this presentation, but I want to say it was in December or January, and it was about between 8:30 and 9 o'clock in the morning. I usually don't get direct sun on my collectors. These happen to be on the west side of my house, and they won't see direct sunlight until about 10:30 in the morning. And I happened to be down in my office and heard my drain back tank running. And I thought, this is unreal, and I went upstairs and looked, and there was no sun on it, so I went out and snapped this picture. It had snowed the day before. You can see the piles that had slid off the collectors the day prior, but those are totally covered in frost, and I was grabbing the ambient energy.
So
excellent.
Okay, next slide, please. So, and this is, how would we cool with the thermal battery system? Is there any, merit in doing that? Yes, time shifting the load to more favorable atmosphere conditions. So one thing that's funny about us is being from the geo industry, the first thing that we always look to is the ground as far as like if we were to say to ourselves, okay, we've identified some merit in using solar collectors to quote charge a thermal battery, and then we can reduce the size of the ground loop. But how would we handle cooling? Because then, the solar collector isn't going to do anything there, and we'd still then need a nearly full-sized ground loop. Well, that's because we always assume that that the ground is the heat exchange element. Whereas if you had a thermal battery and you were trying to cool with it, you'd probably find that the best way to reject energy out of it is going to be with a fluid cooler, and to do it off cycle and at night. And then again, either reducing or entirely eliminating the need for a greater ground loop. In any case, so you're time shifting the load from the time when it's happening to more favorable atmosphere, potentially time shifting it to more favorable utility rates, if that happens to be a relevant factor. It spreads the load out over more time and more potential sink elements. Again, used with dry fluid coolers, or you could use it with a standard DX condensing unit, but then instead of piping the indoor line set to an A coil, you could pipe the indoor line set to a coax coil like you'd find in a water-to-water heat pump. And then you could run that loop off your transfer tank. So there you go. Then you're using an outdoor unit with a thermal battery and rejecting heat energy at night. And theoretically, you can also use solar collectors to bleed heat energy out of them at night, particularly if they were unglazed solar collectors or if they were building integrated solar roofing systems, like what we're trying to encourage some people to recognize. AIT is, I believe, the name of the manufacturer that's building a pretty neat-looking building integrated solar roofing system that can be used with shingles or asphalt shingles or metal roof.
Have you met Bristol Stickney yet?
I have talked to Bristol. Yeah, he's got the that Solar Logic, I believe, is their company, right?
Right. SLIC is his controller, but he also does a significant amount of work and research in night sky re-radiation cooling.
Good. Well, I think it's again, it's one of those things that could use more development, and it's one of those things that if you have the capabilities to utilize it, it could be have some big implications. But most systems don't have the ability to utilize it because they're not designed in such a way to where they could adapt and do such things.
Right. We need to start thinking outside of the box.
Yep. Next slide, please.
Or maybe inside the ground in a tank.
Inside the box, in the tank. There you go.
Just some detail on the Laramie project. The first one that went in, it's 3,500 square foot home. They had a propane forced air furnace. Boo, but whatever, scorched air. The homeowner used 800 to 1,000 gallons of propane per year. They had currently already a 2 4x8 flat plate solar thermal system that was a drain back, and they used that to heat their domestic water. The customer went to the heating contractor, who was a new dealer of ours at Energy Dynamics. I had set him up with a GeoComfort line. And he came up to a training, and I had talked to him about what we were up to with thinking about how these systems could be combined, and he thought this would be a good one to try it out on, and it worked because conventional geothermal ran into dead ends. There was insufficient water. They did not have, you could not do an open loop at this location. Closed loop horizontal was too invasive for the homeowner's liking. That sensitive desert landscape there does not grow back very effectively if you go digging it all up. And the closed loop vertical was expensive. They had quotes from companies actually coming up out of Colorado, Mark, to go up to Laramie and do this, and they were charging a lot. They wanted a lot of money. We couldn't find inexpensive drillers. And so we approached them with the thermal battery idea, and they were receptive to doing it, even though we told them, we don't know what we're doing. We're just going to be guessing, and we'll see what happens. So that's what we did. So next slide, please.
Wake up, slide master. There you go.
So we installed a 2,500 gallon tank. We put 3 700-foot sections of 3/4 inch poly inside it, piped in parallel. We had quite a bit of trouble purging that, had to cut it all back apart again and then purge each loop separately. That's one of the lessons learned. You don't want to try to purge vertically oriented like loops of pipe. They are practically built to not purge.
Guaranteed air binding.
Yeah, exactly. Quite a lot of it when you got 3 of them in parallel, and then but we learned our lesson there. Probably should have learned it before we tried to do it, but we don't like to do those sort of things. 2 flat plate collectors were added to the existing 2, so then we had 4 total. A flat plate heat exchanger was added in the primary drain back loop. So although it's not shown this way in the drawing, the Laramie system is also a drain back solar system. It's just not draining back into the battery. It's draining back into its own loop inside. We did have 1 300-foot borehole drilled. We were able to get that done, and again, that was a guess. We just said, well, let's, we think that it's going to need some ground capacity. We don't think that the 4 solar collectors are going to be quite enough to get it done, and we wanted to see, could we run a 5-ton heat pump off of 1 300-foot borehole, one thermal battery, and the 4 solar collectors. So again, the system's a 5-ton split that was put in there and on top of the existing propane furnace. So propane furnace is still, the fan is still providing the distribution, and the heat pump's 5-ton. Next slide, please. So that's the basic configuration of how it works. Transfer tank is the point where all the energy integrates, and the solar collector or the ground loop can contribute energy into the system, and the battery is this big thermal moderator that allows a 5-ton to run, because obviously you can't run a 5-ton heat pump off of just a 300-foot loop. It wouldn't be nearly conductive enough. It needs this, another good analogous term for the battery would be a capacitor or a flywheel. It's just a big, highly conductive thermal mass that'll stabilize a system, and then the transfer tank can be the point where everything integrates, and the battery can be the place where everything stabilizes. And the fact that it's latent capable provides that much higher capacity than you would even understand if you were just thinking it was just, like if you were just pumping the water from the tank in the ground through the heat pump and so on, you would not get the latent capacity of it because you'd freeze up in the heat pump and then it'd be over. The moment you got to 38-degree water, it'd start freezing in the heat pump because it's going to be, discharging at around freezing at that point, and it'd be over. Whereas if you freeze protect that thermal battery loop, you can pull it all the way down to 25-degree entering water before you're risking locking the thing out on low pressure. Now, the first year we ran it, we had a D circuit coming off of the transfer tank, and we were pumping the heat pump by itself and the thermal battery by itself. We then combined the two the next year because the transfer tank was becoming a pinch point of energy, and although it ran the first year all year long and served the loads, we pulled the transfer tank down into the low 20s a few times, and the heat pump did lock out a couple times and had to be reset. But then after we realized that by hooking it in series to the thermal battery and then allowing the controller to pump that B circuit that goes through the heat pump, whether or not the heat pump was running, that it would solve our problem. And so that's what we did, and it worked well. So now if, for example, the solar collectors are bringing BTUs in real time, they're going to be coming into the transfer tank. We're not going to be running the circulator D down there and pulling heat energy off that primary loop and putting it in the domestic water preheat. We'd just be running circulator E, so running the primary loop, and then we'd be running circulator A, and it would be then pulling it off that loop and heating up the transfer tank. And then as the transfer tank reached a threshold, it would turn on circulator B and take those BTUs out and put them in the battery. Now the heat pump might turn on and run while that's occurring, and it might be getting 50 or 60 degree water, and it's going to be scrubbing those BTUs off the system at that point, and then whatever is the relationship of the deficit or surplus of energy that's left will be going out to the thermal battery to either try to scavenge more energy out of it or perhaps deposit some surpluses that the system has found back in the thermal battery. So as the heat pump is melting ice, the heat pump is creating ice on the heat exchanger in the thermal battery, but then the next day or whenever the transfer tank becomes above freezing, it's melting the ice from the inside out on the thermal battery. So I imagine there's going to be more questions about this schematic, but I think the main thing people should take away is we're not saying this is the way to do it. We're saying this is the way we did it, and this is the way it works, and it works quite well, but I don't doubt we're going to get better at it as we do more of it. Okay, next slide, please.
Quickly, a question while we're at this point. That number one transfer tank, I guess would probably be a question for Colin, is that considered like the equivalent of a low-loss header and also a thermal mixing tank, where you've got the ability to be able to reference what's going on down inside of the actual ice storage tank?
That particular tank is not referencing what's going on in the tank. There's another sensor that goes in tank number 2, but yes, basically that would be your hydraulic separator in the system, albeit done with just 2 pipes, and it's just an intermediary, wide spot in the road for everything to tie together and for those temperatures to blend.
It's what Siggy would call a fat spot in a road.
So, and we would use it like a lot of times we've buffer tanks, like the Boiler Buddy buffer tanks, as that. Obviously, Colin built that awesome-looking Aquatherm one. We would envision there being something like that. I mean, the difference between the reason we're calling it a transfer tank and not a buffer tank is obviously we're transferring various circuits through it, and their source sink side of the system circuits, and in that way we thought we needed a different term than like buffer tank, so we call it a transfer tank, but it's the same thing. So what happened with Laramie? Did it work? We were told it wouldn't, but yeah, it did. It entirely eliminated the propane usage. It saved the homeowner $2,671 this past winter in heating cost. That was calculated by figuring out what the propane costs were in Wyoming over this past year and calculating how many BTUs the system served. And that actually is, and what it represents is what that would have cost with the current electrical rate in Wyoming serving the system, because we know how many kilowatt hours it used and we know how many BTUs it delivered. But it actually is better than even that, because the homeowner installed this PV system at the site, which you probably saw in the previous picture, which generates all the electricity that the home, including the entire system that we put in, is using. So it, in one way, it's represented to save that amount of money based on what propane would have cost this year and what the Wyoming electrical utility rate would have been, but since they offset all of that with on-site PV, so you could really just amortize the cost of the PV over the life of it, and then you could probably represent that differently. Okay, next slide, please. Okay, so the controls, originally when we were doing this stuff, we were using standard HVAC controls, temperature, differential temperature controls and set point controls and just a hodgepodge of various things tied together. And then we used a completely separate data logger on the system, and that's not ideal for obvious reasons. But we switched to this easy system control, which is a web-based, versatile, low-cost, scalable system. It's basically a blank slate. It's not made for the HVAC industry. It's made for whatever industry wants to apply it, really, any kind of manufacturing or whatever. So they don't, they don't support it, the end use customer. So thermal battery systems decided we would do that, and we do. So we have these controllers in stock. They're blank slates. They'll do anything anybody can think of. If you can define it, if you can come up with a conditional statement, then that's as good as done. We'll write it into the control sequence, and that's what it is. It's just managing inputs and outputs over the internet. Now, it doesn't have to be online to work, because once we write the program onto it, it can be standalone and can be unplugged and not be online, and it'll still carry out its script locally. But it's fascinating to have that kind of control over systems and to gain an intimate understanding of how they work. I absolutely just obsessed over the Laramie system, watching it go. I'd log on, look at the weather data for the day, and try and figure out how much solar gain we were going to have, and just watch it minute by minute functioning. And you can really gain a level of understanding as to how these systems work when you can do that. And if you don't like something about how it's running, let's say you came up with a control sequence that you thought was going to work. If you were going to share the solar with the domestic water, and then you were going to go back and put the solar into the battery, and then you decided after you didn't really like how you were doing, no big deal, just go change the sequence. So the main controller there is sort of, it's a network supervisor. And so within that main controller, it'll simply do 2 relay outputs and 4 inputs. And they could be CT sensors, they could be temperature sensors, they could be flow meters, whatever you were trying to monitor. And then when you go beyond that main controller, you choose which open protocol network you want to use. Well, you don't choose that, because there's just 2 networks. There's microLAN and Modbus on there. And the Modbus network, Modbus is an open standard protocol, so you can go buy. We have peripheral devices, input-output devices, but there's other stuff on the market that people could choose to use also. So you're not getting married to any particular proprietary system with stuff like this, and we like that. So that's
James,
where we're at with
questions for you. How many points of input and output does this have?
That one's expandable to 40 and 40. But then it's also expandable to another network supervisor, so more than one can go on it. So effectively, it's infinite. But for one network supervisor, one of those boxes right there, and then we'll see a screen here later on where you're looking at the control status and whatnot. We can add 40 inputs and 40 outputs into one system network.
So it comes off shelf with the ability to go 40 in, 40 out?
Right, but there's not 40 outputs or inputs with that main supervisor. In other words, the terminals aren't there on that one. There's only just 2 outputs and 4 inputs. But you then plug into another device, and we can expand out to another, like the main device we use is a Takeo IO. It's a different Takeo than the green pump company, but they make a device that'll do 10 digital inputs, 4 analog inputs, and 10 digital outputs, I believe. And then, I think that's what it is. I don't exactly
This is limited only by your imagination, which, if you've ever seen my imagination, is pretty scary.
Exactly.
I have something similar to this up here in the mountains, and I allowed the manufacturer of the software to go in and take a look at it one day, and he came out and started seeking psychological help.
Yeah. Well, it's a difficult thing, because I'm not the best at working through these sort of technological advancements, but I am at least I'm aware that what sort of implications they're going to have on our industry, and I think that they're profound. And I think if we just try to hide from it, it's going to be that's not the solution. The solution is to try to figure out how we can, as an industry, can ensure that as this technology is coming down upon us so quickly, how are we going to try to respond to it? So here's this is a system actually that's in Ennis, Montana that we're looking at here. This one has a seasonal thermal energy storage component where there's a 340-foot borehole that's going through entirely dry granite, and we're routing solar thermal down the down the borehole, and have been for the past 3 months. And we've heated it up to about 65 degrees right now at the center of that borehole, and we're already heating here in Montana. So it's now plateaued at that spot. We'll see how low it gets over the winter. But this is just an example of what's leading into the next part of this presentation, which is hopefully I'll try to go through quickly because I realize it's not on the front and center of the RPA, this technology that we're talking about, but connected devices and the ability to process it is the new wave of technology, and it's coming very, very quickly. As a matter of fact, it's pretty much here now, and this is an example of it. We're not talking about a connected thermostat here. We're talking about a system to where we have 30 connected device inputs being monitored and 10 outputs managed, all online, and a lot of this stuff is going to be defined by some simulation programs that we've got, which is called Trinsis. We had them build us a custom simulator for these things, but we're actually building we've got another project going on where effectively we're going to want to, these systems are going to be built in the virtual world. They're going to be tested and run in the virtual world, and there's going to be analytics running on the controls and on the system performances, and artificial intelligence is going to be defining how system configurations ought to be defined so that we're not out physically doing it in the real world and then monitoring it. We're just doing it, in the virtual realm and then just completing the real world systems after the fact. So,
Rich McGrath had a question for you real quick that's kind of relevant to this. He wants to know how many BTUs has he stored in that system, and I think in this vertical borehole system. I don't know if you tracked it or not.
It's not even on for some. Unfortunately, this screenshot right here isn't showing that, but that is being logged, and it's at the bottom. But there was an issue with the data logger, so I actually have to combine 2 sets of data from when we were logging it previously, and then I discovered or caused an intermittency that then, I don't want to get too far down that road. But the problem is we have those answers, and we put tens of millions of BTUs down that borehole, and I don't know off the top of my head how many that was right now, but we will get our stuff together and be able to produce a report about this entire system at the year's end after we can really process all this data. We're bringing we're bringing more capacity into our organization to process this data, and we're going to get better at it. We're better than we were, but we're by no means good at it.
Well, you're pioneers. Once you get those arrows picked out of your back, then you'll be able to answer the questions, right?
Yeah, hopefully.
Correct. Stay tuned. More interesting things are coming from the crazy minds at Thermal Battery.
There you go.
Yep. And we don't doubt that there's going to be a lot of other people in this space doing what we're doing and better. But we're doing the best we can with the limited resources that we have right now.
I had breakfast with Carol Fay, who works for Wiesmann now, and her boss, and she said, yeah, this ice is the next big thing coming over from Europe. So they've had
Wiesmann owns Solar Ice, which is the German company that we discovered 1.5 years ago that Colin, you guys told Colin about it. Somebody within your organization told Colin about it. Right, and when we found that, we were quite intrigued by what they were doing. I've tried to reach out to them a couple of times. They're not interested. I don't know. They haven't responded. But they're going about it with Solar Ice and IsoCal is owned by Wiesmann now, and their system is sort of a proprietary, iteration of what we're trying to do openly. We're just saying it's just heat exchangers and cistern tanks, and we're calling them latent capable thermal batteries, and we think they have big implications. We're just going about it in a different sort of a way. But yeah, Wiesmann does obviously believe in it, or they wouldn't have bought that company.
I like your style.
This is the Ennis system. As you can see, it's pretty similar to what was going on in the Laramie system, but it's not a scorched air system, which is awesome. It's a It's a, all radiant distribution. They have an electric boiler if needed. We do not suspect it's ever going to be needed unless the heat pump breaks or something. But right now that 300, it's not a 300-foot loop, it's 340 foot, so that's a little bit wrong there. And like I said, we've been pumping solar energy down that borehole for 3 months now, and we heated it up to 65 degrees. So if I'm running that circulator C and I'm testing the temperature that's coming back into the transfer tank at that number 5 location on there, if I'm running it all night long, the coldest that it gets down to at this point was about 65 degrees. So that's representative of basically what the center of that borehole is when there's no contributive or deficit thermal reaction to it. It's just that that's where it's at, which is pretty exciting. It's a lot of heat. That's a big column of rock we've heated up.
So are you doing a direct extraction off of that into the heat pump and then into the space heating system? You're not using the ice storage?
Well, this system may never get into the ice storage. That's correct. We don't know. Right now the batteries are about 55 degrees, and the borehole, again, is we've just been banking energy down that borehole all summer long, and we'll see what happens. This home is very well insulated. It's about a 4,500 square foot house, but it's very well insulated, and it's only going to be partially occupied. The owners are coming out of retirement and going to be moving into it, but they might spend a good portion of the winter at their current home in California. And so if it's not occupied, they may turn the heat down and let it just sit there at 60 degrees or so. So the loads aren't necessarily for the first couple of years going to be representative of an occupied structure. So it remains to be seen what these batteries will get down into. We saw on the Laramie system that we pulled into and then out of that latent condition 4 different times throughout the winter. So it's always a matter of, of surpluses and deficits. And so what we're learning is how can site-derived energy systems be configured so that we didn't invest so much money on the front end in those active energy infrastructure elements to where we're, anybody could design one that would do just absolutely amazing if you put enough source energy element in it. But what we kind of want to define is where's the bottom, and what's the minimal amount of source energy elements that we could put in would still meet a, let's say somebody would set an arbitrary COP set point and say, I want this system to achieve an annualized COP of 3.5 or greater. Or let's say they moved the bar up and they said it needs to achieve an annualized COP of 4.5 or greater. Well, what we want to get to the place is being able to identify and define how those configurations can be built, can hit those marks, because that's what we think the prize is. That's what the race is.
Interesting. Do have one quick question for you here, and this came from Rich McGrath. It says, could we use the battery connected to a coil to remove latent from the home alongside radiant cooling, removing the sensible load, and remove a chiller and some refrigerant?
That's probably a question best answered by Colin.
Yeah.
Colin's our resident subject matter expert on hydronics and refrigeration, so I refer it to Colin.
Would you repeat it, Mark?
Sure. Could we use the battery connected to a coil to remove latent from the home alongside radiant cooling, removing the sensible load, and remove a chiller and some refrigerant? And I think what he's getting at is basically the ability to be able to use these ice storage units to provide not only sensible but also latent cooling within a space. And my thought is yes, because my experience with radiant cooling is that you're looking at temperatures typically between 50 and 70 degrees Fahrenheit as your approach temperature to your actual radiant panel cooler. So
yes,
obviously it would work. You'd have to put a mixer in there to keep that temperature high to avoid dew point. But if you had a fan
correct,
coil, then you'd be able to run 35 degree Fahrenheit water through there and do your dehumidification.
Now, early in the spring, early in the summer, I would totally agree. That's exactly what would happen. Now, as the summer wears on, depending on the severity of the summer, I can see where your battery, case in point, my own at home, right now, I believe, is 80 degrees. 80, I didn't look this morning, I should have. 80, I think I want to say it's about 82, 83 degrees. And at that point, you're not going to be able to do any latent cooling load with that temperature of water. In fact, you're probably not going to do any
sensible. Yeah. Okay. Well, back to you, James.
Okay. And so this system was installed by Baker Light Industries, Wayne Baker out of Alder, Montana. And he's actually done several of these battery-type systems, these variants. Yeah, that's it. Next slide. So that's the project. We used two 1,150-gallon cisterns, and we put one Hyperloop in each. And that's because they were available. We sourced them locally. If you said, "Oh, I want a 2,500-gallon cistern," okay, well, where are those? Well, they're at various places in the country, and it didn't work out conveniently that we could get them. So we said, well, what about two of these? Well, that works fine. They are available locally, and the Hyperloops they were designed for pond applications, but they work great for going in these tanks because they just go right in the manhole cover, and then we build a PVC rack system that gets trapped into the corrugations on the tank that holds the Hyperloop up. So it's just in this kind of snail uncoiled formation in each of them. And real painless and easy process, a lot better than trying to wrestle a 700-foot loop of pipe through the manhole cover. That's a pretty ungraceful, sweaty process, and we've done it, but this is much, much easier.
That always works nice if you have 3 men available.
Right, and we came up with a method that we think we could do it with a pipe uncoiler and then routing it around a pipe that's suspended from the top so that you could just put a pipe uncoiler up on the forks of a forklift above the tank with the coil perpendicular to the tank, and then somebody could be down in it and routing the loop over like a PVC pipe that's hanging along the top. And I think that in theory, we had that theory, and then we nearly dropped the forklift on Colin, or something happened when you tried that.
That's pretty.
I heard a big noise and the coiler fell off. It wasn't good. Anyway, I don't doubt that other people could pull it off. But Hyperloops work great. And okay, next slide, please. Okay, I'll try and go through this fast because I know most people on here are either going to be not interested or downright opposed to it. But I think it's got big implications, and I just want to discuss why we think that they are a big deal. So we say within our organization a lot, if I had more information, how would I respond? Is there a better way to do that? And imagine if you could take the collective knowledge of the entire RPA and have it applied to an installation. It's obvious that that installation would be representative of the very best in hydronics that could be. And what's amazing is that that's sort of what's happening with this connected world that's going on. There's a collectivization of knowledge and wisdom that can be gleaned from what's going on here, and despite it also simultaneously being maddeningly confusing. Next slide, please. So, just put this into perspective, 90% of the world's data was produced in the last 2 years. So 2011 was a very long time ago in the world of big data technology. So,
and this is probably because I left all my computers on. I'm sorry, guys.
Yeah.
They gleaned it off of yours, Mark.
Yeah.
So some figures: in 2013 there was approximately 9 billion connected devices in the world, and it's estimated there will be 50 billion connected devices by 2020. And the majority of those, we went from connected PCs to then being mobile devices, are now surpassed computers as far as being the connected devices. But the ones in the future are M2M, so machine-to-machine connected devices. So these are just it's the Internet of Things, or as Cisco describes it, whatever terminology that's going to come out the other side of it. Some people call it the Internet of Everything. But what is the implications of 50 billion connected devices? That's the main point here. Next slide, please. So I don't exactly know where I pulled that figure from, but again, just simply showing we are very, very big. Next slide, please. And it's not the sheer volume of data that we're talking about, but it's the ability to process it. That's why the implications are so large. And my snarky little comment here is, you know, we may discover that turning up and down the thermostat is not the only action we can take in response to all of this information. Now, obviously, the RPA does something beyond that in that employing an outdoor reset curve and adjusting the supply water temperature to the load is obviously an action that can be taken in reaction to, knowing more about the load, about the nature of it, about how it's happening. But what isn't being done, and what's incredible to us, is if you think about the way the industry is aware that there's connected thermostats and that they'll use, geofencing to determine whether or not by connecting a person's smartphone to the system, it will know whether or not they're in the room or not. And they'll use that occupancy data. But what do they do with it? Well, I guess you're supposed to just, turn the thermostat down when they're not in the room so that that zone gets into an unconditioned condition, then get it back into the conditioned condition when it's occupied again. Whereas we're amazed by where they're not looking. You can adapt things on the source/sink side of the system in reaction to what's going on with the loads and the sources of energy that are in the environment. That I think that once that's revealed and it becomes self-evident, there'll be a tremendous amount of focus outside the space. Next slide, please. So what are some of these itemized implications? That the thermal battery system, I'm not going to go through, I'm just going to talk about these things and people can read them, but the point is that people would say about our thermal battery proposition would be, they'd say, James, you got to keep it simple. That's too complex what you're trying to do with all those various moving parts and pieces. We already have enough trouble on the front end of our industry to actually ensure that we can pull off good installations and that there's not these black eyes out there. And here you are adding all this complexity and everything else into it. And what I would respond to is that the front-end installer is not going to be asked to deal with these complexities, that they're going to be moved into the back end, that they're going to be handled with processes, in technology, and that the front end of the system or the front end of the industry is going to be more about following a procedure, following what was defined by a back-end process. And I think that's just the natural way it's going to go. And I know a lot of people don't like that, and they wish it, they want to stay control. That the HVAC industry doesn't like the fact that technology is getting a hold of their customer and getting directly in the door to their customer. But I guess my point would be is that the technology does not go where it's invited. So next slide, please.
The only exception to that rule would be Target stores and Home Depot, where the hackers made it through their HVAC control systems into their cash registers.
And again, I mean, I don't deny that there's all kinds of difficult things that are going to be relevant liabilities that are out there because of where things are going. But I guess what I'm saying is it's not going to stop it. It's not as if Target and Home Depot are going to all of a sudden say, we're not going to connect to the internet anymore.
Yeah,
we're
done.
Yeah.
You got to bring cash.
Right. So, smart home futures. Again, the technology industry understands that moving energy around in the home is somewhere that they're looking at, and they're talking about connecting these things. But I don't see them preparing things outside the home, which I think once they see that, there's a lot to be done out there. So that term, building integrated active energy elements, I'd like to see more discussion and development around that idea, that instead of building energy efficient structures and then stopping the discussion or the idea there and then moving to, quote, efficient HVAC, we know that the money spent on good insulation and good windows is well spent because those are going to last for the life of the structure and they're going to mitigate the energy loads. But then we skipped the other thing that could be done, which would be building integrated active energy elements, which are not passive like windows and insulation, but actually systems that can respond to the sources and sinks of energy in the environment and can move energy around. Start pumps and circulate through the roof. I've got a temperature sensor on my roof that I keep an eye on all the time, and it's just incredible the sort of abundance of energy that there is up there all the time, including in heating times of the year. My roof is often in above the temperature that I need the inside of the space to be, and yet I'm burning natural gas.
Yep.
Okay, next slide, please. So site-derived energy systems use active thermal energy infrastructure to reduce the amount of generated energy required to condition the space. So there should be two ways to think about this. Energy that can be site-derived does not need to be generated, just like energy that can be generated does not need to be site-derived, but which one is better? The word generated has an implied change of form, and derived, the form stays the same. So at the end of the day, the energy required to heat and cool our homes is thermal energy, and that energy can be site-derived from the environment around the home. And it ought to be. And all tools are not hammers, so the ground is not the only place to source or sink energy. And because of the tremendous variabilities of the environmental conditions around the home, the system ought to be able to adapt itself and use physics to sort of play judo, play judo with the loads, use it against the loads. Okay, next slide. So currently there is no such thing as a multi-source / sink system that is configured around an intermediate thermal storage and exchange foundation. There is only air source heat pump and ground source heat pump. If we're talking about, and if I'm going to take off the table the idea of importing fuel and changing its form to create heat, so if I'm going to say that the game is moving heat around and that there's only two things that move heat around, there's air source heat pump, technology, or air source heat pump industry, if you will, and then there's the ground source heat pump industry, which, as we said, we think that there's room, lots and lots of room to find out that those are two single source methods that are myopic and clumsy, and you don't have to get out of bed all that early in the morning to find ways to beat them at that game. So, and then simultaneously to that reality existing, the technology industry is focused on connecting your thermostat to your toaster and your refrigerator. They're looking inside the space, and they're going to keep looking in there, but I guess the main point is energy is a pretty big deal, and it would be crazy to think that the technology industry is going to not figure out or not get further and further and deeper into the HVAC industry, and we should just be aware of that. So that's, are we working to be a disruptive force in the industry? Yeah, we are. We're trying to identify better methods of moving heat around, and we think that there's several that the industry ought to be looking at and embracing, and that's that.
Excellent.
So,
this is some pretty earth-shaking stuff that you guys brought to the table here.
Yeah,
Appreciate it
I'm
very
really
much.
impressed. If you want to be disruptive, you've certainly disrupted my brain cells this morning.
Yeah.
well, I'm happy to take questions, and I realize that we make some pretty bold assertions with the stuff that we're trying say here, and you know, it is what it is. We do believe the stuff we're talking about, and but we don't believe that we're the best at it. We just think that that's we want to encourage more people to do it.
Yeah, we live it, and we've you know, we're playing with our own first. That's what's always fun about this industry. You know, as your home is, Mark, you know, mine is my testing and proving ground, and so you try it on yourself first, and if it don't work, well, you don't put that out there.
Well, we do help our family.
Go ahead, Dave.
I had a couple of questions for you guys.
Yep.
One of which was that came to mind. Is there any need to monitor the water level in these tanks and add water over time?
Great question. Yeah, I mean, we want to keep them to within 10% of the top, because the expansion of the water when there's ice around it, what you don't want to do is have a situation to where you're pressurizing and possibly splitting or causing any kind of issue that way. So, yeah, we have dip tube, you know, lower a tape down inside it, measure the water, and go from there.
And those automatically answered my second question, was how do you deal with the expansion from ice?
Got it.
That you don't want to be. Now, I can speak to that one because of experimentation that we've done on my system. Last winter, case in point, we were going to duplicate the performance, or try to duplicate the performance we had the year prior, and so I'd shut off all solar input to my tank in October, and we were letting it pull down, and I'm running my control manually rather than with the automatic controls that we have here, or showcased here. The tank was running along fine until I went down on December 12th to get a beer out of my fridge in my basement, and wondered why my drainback tank was running at 9 p.m. at night. And went and checked temperatures. I had proceeded to burn up a circulator and changed it and went to prime it, and there was no water there. And I had literally froze up my battery. So I got on my data logger and checked it out, and I went into the latent phase on October 31st. Actually, I had shut off solar to that quite a while prior. I'd have to go back and look at my records, but this was December 12th. I ran October 31st to December 12th, totally in the latent phase. Had to, at that point, fire up reluctantly, a propane boiler on my indirect fired heating system to develop enough hot water to get a path cut through the ice so I could fire the solar back up and thaw this again. When everything thawed out and got back into the totally liquid phase, which took a month and a half, I believe, to get me there, I had to add 160 gallons of water to bring my tank back to full. So it expanded, pushed out the lid, which my tank is buried 100%. I don't necessarily recommend that. I do have a gauge tube that's piped onto mine that comes into my house so I can see what it is inside my house. But where the lid is not fastened down, and I insulated over the top and buried it, and it pushed that water out of there. A concrete tank, if you look at the solar ice product, will use a tapered cone type lid on their tank so they can take care of the expansion into that cone and always stay at their 100% fill level. They've got some excess real estate in there to handle that expansion.
James, I had a
What's
question.
the recommended depth of burial for the batteries?
The manufacturers have their own. Yeah, it's anywhere from 28 inches to 36 inches, depending on if it's a poly, like there's Norwesco, Snyder, and Ace Rotomold are three of the bigger ones. And they have a maximum burial depth printed on the top. But also, it's worth understanding that that generally represents what it can be buried to and not crush when the tank's empty. So you could, you know, if we would just say people ought to follow the manufacturer's recommendations as far as what it needs to be buried at. But if you were to fill the tank and make sure it stayed for the most part full, you could bury it deeper. And also, if you're going to be taking up some of that burial depth with some insulation on the top of it, you could potentially go, you know, that much deeper with it also, because you've got not that much weight with the insulation. So.
You work on weekends?
Do you have any more questions for him, Dave?
No, I'm good.
All right. Well, I need to tell you that Ross Pickett won the contest about where the hell I am. I'm in Heaney, Colorado. Ta-da! Google that. You will see the country that I get to see on a regular basis. And I've got a couple of questions that were raised during the actual presentation. Rich McGrath wants to know from James what the status is on your wet sand storage system.
I actually talked to Dwayne Crawford this morning. He's putting that in Nebraska, and the status is he's putting it in. The issue is that he was trying to talk about this morning. The questions had to do with the layout of the hyperloops in the saturated sand battery, and originally he had planned on standing them up, and at this point he can't because he's not going to be able to get a conveyor, and so they're just going to have to backfill it with just dump trucks and moving the sand around by hand. So instead he's going to layer the hyperloops in like lasagna into this. And so in my point, my only comments on that were, effectively the saturated sand battery idea is, and somebody could go on the multi-source heat pump site and see that in detail, but the concept is that, if we're talking, why thermal battery systems, why do we say that water is the best thing? And we went through some of that latent capable aspects and so on. But so if water is the best thing to store and exchange energy with, then what is the cheapest container of water? Is it a concrete tank? Is it a poly tank? What is the way to do that? Well, one other way of looking at that would be sand is a container of water, meaning you could take a bunch of dry sand and pour water into it, and the sand would contain the water. Now, the water could get out of the sand from capillary action being pulling it out, or it could evaporate, but not if you vapor barrier it. So the idea was, what if we dig a hole, line it with a vapor barrier, put heat exchangers in it, dump sand in it, and then saturate the sand? How much does that cost per gallon of storage? Because we don't need the liner to contain the water. In other words, the liner could get punctured, or it could have an issue in it here or there, but it doesn't mean that all the water is going to go rushing out of the sand. It's capillary, it's held up by the molecular tension of the sand. Anyway, yeah, so the idea was, so what would that cost? Well, a poly tank costs about $1 a gallon. Maybe a little less than that, but shipping and whatever, you might be into it for about $1 a gallon. And concrete tanks are probably going to be 60, 70 cents a gallon, but then you've got also, site handling aspects there, whereas a poly tank, you could, just haul it up there on a car trailer and kick it off the trailer and drag it over to the site and throw it in the hole. It's, they're lightweight and easy to move around. But the sand battery, I do all the math on the multi-source heat pump group on LinkedIn, but essentially we can store water for about 30 cents a gallon with sand. So the status is, yes, there's one happening right now. It's happening in Nebraska. It's being put in as we speak. But it's a cooling-dominated application, so it won't get into these sort of issues of the ice that we're talking about. We do not anticipate that at all because it's a restaurant. It's got a lot of cooling demands, not a lot of heating loads, and we don't believe it's ever going to function as a latent aspect. And then that's one of the concerns about a saturated sand battery, if it's used in latent, would be you're going to frost heave that area very significantly. So obviously you can't put it underneath like a foundation wall or under the driveway, but it would be an inexpensive way to build a consistent and highly thermally conductive and highly thermally capacitance thermal battery. So
okay, great. That sounds like even more new innovation coming in. Harvey Raymer asked a question. He said, if we apply a vacuum to that small system, if you had a totally closed system and you could apply a vacuum to it, you would raise the freezing point. Would there be any advantage to doing that?
I don't know.
Maybe even get the freeze point of the water equal to that of the ground that it's connected to.
I don't know.
Interesting concept. Holding a vacuum is harder than holding pressure, so developing that tank and system to do so would be quite intriguing unless we can create a light bulb. But interesting concept.
I've heard vacuums suck anyway, so I always stay away from them.
Pun intended.
We had one other comment that was relevant to this, and this is from Rich McGrath. And Rich, we could have a whole discussion on this alone. It says, nobody in my area designs thoroughly. Wow, really, what a concept. This is the single largest problem when partnering heat pump systems with anything. What do we do to eliminate these issues? And he wants to know if either Colin or James have any suggestions. Our association, the organization, the RPA, is in the process of requiring certification of designers and installers. This is not going to keep people from working out of the trunks of their cars. This is not going to keep people from doing the wrong thing, but it's a step in the right direction. If we can get recognition, not just from the consumer, but also from the authority having jurisdiction, then we lessen the chances of having loose screws floating around out there that are doing things that really shouldn't be done, that are, they consider themselves pioneers in the field, and I guess everybody's got to do some experimentation. But do you guys want to have any input to that?
I would just say that for our purposes and what we're doing, what we're hoping to do is to create a foundation that will allow people to go and refer to stuff that we've done in the past so that we can reduce the amount of experimentation needed. Or in other words, keep the production of development and innovation on the forward edge and not constantly be just redoing the same sort of experimentation over and over again. And if we can actually make progress with identifying scalable aspects or best practices with these multi-source approaches, that there can be, we as an industry, as the whole broader industry, solar thermal needs to be talking to geothermal, and they don't. Those two industries don't know each other at all, and it's bizarre, but they're. The point is, I think we ought to be staying in communication with across multiple industries and sharing knowledge as we're doing it, so that less blind invention has to be occurring at the expense of customers.
What we're trying to do is build a system so that the rest of the industry can work that system. You find something, we take the experimentation back out of it again. And hopefully somebody else along the line in later years comes along and continues to think outside the box and make improvements. That's all part of the whole structure and game. But I love to experiment on things, and there's more kindred spirits out there to do that same thing. But once we get this perfected and be able to model things and say, this is your project, you need X number of solar collectors, you need this big of a battery, you need this big of a multi-source heat pump, you need this much radiant tubing, you need this much of a fan coil for the latent load, and everything, this system works. And it works by itself and works very economically. And we've got all these players in the game that have become a system, and basically take it out of the box and install it.
And that's what technology is going to make a reality that was never able to be done before with any true level of conformity. And so I'd say that conforming systems is what is sort of the definition of what the future, I think, holds, is that, you know, somebody could do a manual J on a structure, and depending upon a lot of the front-end detail about how that thing gets put together, you know, it's the best we've got to estimate that. But the promise of big data and connected systems is that all of a sudden you don't have to sort of do a lot of work and math and figuring out how those systems are going to perform and respond, because there's going to be just an abundance of information about those details, so that conforming systems can be put in, and that the process that was very complex and difficult on the front end can get moved into the back end, and some clarity can get formed about it all from a higher altitude.
Yeah, and by the way, I was corrected. That was John Langan that had asked some of those questions. He was using Rich's computer, but thank you both for your input in that. In any case, some good news is that the RPA and IGSHPA have come real close. I'm waiting for a signature countersign back from the executive director of that organization, but we've signed an MOU basically agreeing that we will move forward and exchange information back and forth as it pertains to us showing their people how to do low temp application, and as it pertains from them showing us how to do ground source heat pump, which they're considered the experts in. But I see this technology dovetailing right into it quite well with the RPA, so we do have an open door. And also the folks over at HeatSpring gave me the names of some contacts of some people that have done instructions for them, and these guys are very open-minded. I talked to them about our reverse snowmelt systems, and they actually got excited. They said that would be fun to model. So it is slowly but surely moving forward. One last comment was that inspectors will be a huge part of new technologies and should be more readily allow innovation as long as there is no hazard present to the public at large. And that is another huge problem, and that's also an issue that we as an organization intend to address, that most of these inspectors are very intimidated by these mechanical rooms that they walk into. Hell, I'm intimidated by some of the mechanical rooms I've been walking into, and I've been doing it for over half my life. So by training these inspectors to be more comfortable with the technology that they're looking at, then it's going to allow them to understand what it is that we're doing, not be intimidated, and leave the door open for innovation like you guys are bringing forth to the table here.
Well, it was definitely a pleasure to be able to get on here and present to you guys. I'm honored by it.
Yes.
Well, we appreciate you guys
taking your time to share that with us.
Yeah. I'd like to thank my co-host Dave Yates and Colin and James, of course, and all of our attendees for having attended this course. And it's open for Q&A now, but like happened the first time we did this, I suspect we probably won't get any questions because the folks that are here know what the heck they're doing, which is great. But if they have a question, by all means, send it in to us real quick. And while I'm waiting for someone to send in a question, I will tell you who's up next. John Barba and some of the other Taco Comfort Team family members will be our guest on October 23rd at 12 noon Eastern. Should be a very lively and interesting discussion in regards to the application of Delta T versus Delta P pumps. There's been quite a bit of controversy going on between myself and Dave and everybody else in the industry about, wait a minute, that's not the way we were taught to do this. And John will be here so that we can school him and ask him questions. And should be an interesting conversation. He was supposed to have been here today, and thank you to James and Colin for stepping in. As we were leaving our directors meeting in Nashville, I had mentioned that Barba was the next person that was supposed to be up, and Mark Chaffee, who's the chairman of our association, grabbed his PDA and started looking at it. He goes, ain't going to happen. I said, what do you mean ain't going to happen? He says, he's playing golf with me that day. Okay, boss. Understood. Certain priorities. So I see no questions on the screen here. And I think that we have chewed up enough bandwidth and airspace. Again, I would like to thank everybody for having attended and contributed. If you've got any questions for these folks, and I'm going to go back to that screen that had their telephone numbers and information on it, feel free to contact them. And if you have any suggestions as it pertains to the show, feel free to contact me. And I am now going to release everybody to go back to their Saturday fun, and I look forward to seeing you guys all in the next 2 weeks.
Thanks, everybody.
Thank
You bet.
you.
We'll talk to you all later.
Take care.
Bye.